Yes. Can you hear me?
Yes.
Is my voice clear?
Yes. Okay. Yes. Please go on.
Thank you. Okay, let's start the next talk. And good afternoon. I'm Nobuyuki Takegawa, and attending online from Tokyo. And it is my great honor to chair this session as a moderator. Let me briefly introduce Professor CHEN at the National Taiwan University. Professor Chen received his PhD degree from the Pennsylvania State University in '92, and he joined the National Taiwan University in '94, and he is now a distinguished professor of the university. Professor Chen's research includes comprehensive studies on cloud, aerosol microphysics, air pollution, and aerosol cloud climate interaction, and by using the regional global climate models as well as ground and satellite data. He served as a member of the International Commission on Cloud and Precipitation. So today, he will give a talk about the aerosol effects on weather and the climate through interaction with clouds. So Professor Chen, please start.
Good afternoon. Thank Professor Takegawa for your introduction. My talk is similar to the previous talk, focusing on the aerosol effect on weather and climate. And the aerosol particles are very small, but they have a big impact in many aspects. For example, in this conference, most people talk about the health issues. But I will focus on the other two issues, that's the effect on climate and also the effect on the hydrological cycle through the weather systems. And such effects proceed through the interaction between aerosol and clouds. Okay, and because it's indirect through clouds, so we call those indirect effects. So my talk will focus on the indirect effects. I'll give you several examples on the aerosol effect on climate and another examples on weather. So the two examples I'm giving is from the study of our group and of my collaborators. One is on the summer monsoon, the other is in the winter monsoon. Both are over this region, the East Asia region. These three diagrams are from IPCC previous report, and they showed very homogeneous, well-mixed greenhouse effects globally. The highest temperature is near the equator, and sorry, this is our forcing scale. But for the indirect effect, it's very inhomogeneous, very locally distributed. And this figure shows the direct effect, that is aerosol particles directly scatter the sunlight back to the space. Then you can identify the major emission regions here. And the panel on the right is the indirect effects. The indirect effects, of course, related to aerosols. So you should have a similar pattern as the direct effect. However, you can still observe a lot of differences. For example, in the Northwestern Pacific region, over the oceans, you still see a lot of cooling effects compared with the direct effects. So what happened in the indirect effects? That's the main motivation of my study. And I did a global model simulation using the community Earth system model. And my experiment is done like this. The scenario is 1850, that's before the development of the anthropogenic pollutions in the Asian region. And another simulation is I put in the anthropogenic emissions in year 2000. Okay, so the difference will represent the aerosol effects from East Asia emissions. And the model simulation conducted for 80 years, but I used only the last 40 years results for analysis. And these figures shows the difference in aerosols. So we see a lot of anthropogenic black carbon, sulfate, organics. Okay, and the natural aerosols are also affected. Some area have more dust emissions, and some area has less sea salt or more sea salt emission. But I'll focus on the anthropogenic particles. So you can see that most of the anthropogenic aerosols are located in the continental East Asia region. And the top diagram shows the aerosol optical thickness. That is what the satellite will see from the space, and also see by the sunlight. So if you have thicker optical thickness, it reflects more sunlight. So generally, the aerosol thickness is around the source region, but also a little bit transferred downstream in the westerly. Okay. So with this aerosol scattered sunlight, you should see reduction in solar radiation. However, this diagram shows the reduction in solar radiation on the surface. You can see the very broad area of reduced solar radiation compared with the aerosol optical depth, especially over the northwestern Pacific Ocean. So what happened here? Okay. Another question is, okay, so if the sunlight is reduced in this region, the blue color area, then the surface temperature is also decreased in those areas. And in contrast, there are some regions with increased solar radiation. That is because of the reduction in clouds. Okay, so you should see warming in this area. But if we look at the surface temperature, it's not the case. Okay, there's a widespread cooling in East Asia, much broader than what's reflected in the solar radiation. Okay, and even in the area with increased solar radiation, we still see cooling. So what happened? Okay, and that's the main question I'm going to ask in this research. So let me briefly explain what happened here. Okay, let's start with the shortwave radiative forcing here. Okay, the additional cooling, additional reduction in sunlight you see here is from the indirect effect, because the aerosol entering the clouds here. Okay, this is a summer case. So in the summer, I mean July, August, June, July, August, there's a stationary, semi-stationary front system over here. We call it the Navy system in Taiwan, but in Japan called Baiyu, and in Korea they call it Chama. Okay, so a large cloud system persists in this region, as over here. And also this region is downwind of the aerosol emission source. So of course, a lot of aerosol will get into the clouds here and make the clouds more reflective. That's why you see a lot of surface cooling here. So that solved the first question. But how about this area? We see a lot of cooling here, even if the radiation is increased. This proceeds through a dynamic feedback process. First of all, the initial cooling produced by the clouds here make the surface air cooler. The cooler air will make the pressure higher. So you increase the high pressure. And the yellow line here is the original Pacific high pressure system. And the cooling also occurred near, almost overlap with the ridge of the high pressure system. So in a sense, it enhanced the high pressure system. Okay. This is the wind fields in 1850. That's before the industrialization in East Asia. Okay, and you can see this is the high pressure system before the aerosol effects. Now the cooling here enhanced this circulation. So you see, this is the easterly wind, and so you will see stronger easterly wind in this region. Okay. And the stronger wind here will cause evaporation faster evaporation of sea surface. So it makes the ocean temperature cooler. Okay, and because it's cooler here, and that also enhances the high pressure system here. So it's a feedback process, broadening the high pressure system. So then the effect can propagate through the mid-latitude to the subtropics. Okay. And this is the wind field change. I don't know if we can see it clearly. Okay, the arrow here is the easterly wind. Okay, and the color indication of the change in wind speed. Red is increasing wind, and the blue is decreasing wind. So this is all stem from the enhancement of the high pressure system, was in the stronger easterly. But here the original wind is easterly, so there's a enhancement. However, over here is the westerly, original westerly here. So the easterly easterly anomaly tend to counterbalance the westerly here. Okay. So this region experiences stronger wind and lower sea surface temperature. Okay. And that's the cause of the lower temperature in this region. So besides the temperature change, are there other effects from the aerosol influences? We already mentioned about the wind change. Okay. The left panel is the wind near the surface at 850 hectopascal. It's about 1.5 kilometers above the surface. This is the before the aerosol influence. Okay, and this is the high level wind. You can see the very strong wind here is the jet stream here. Okay, so that's the original wind field. What happens if we add in aerosol? This is the same diagram as shown before, but I give you more details. Okay, increased wind here, decreased wind here. However, you also show high, low pressure perturbations. Okay, it's called a wave trend. Okay, a wave of high and low, high, low. And that can induce some dynamic feedbacks I will talk about later. And the wind also changed in the high level, in the 300 pascal. This is original jet stream, and these are changes. So you see the location below the original, south of the original jet stream has stronger winds. And to the north, there's a weaker wind, which means the jet stream shifts southward. Okay, and I think the shifting south jet stream is related to the production of the low pressure belt here. They are locked together. And this low pressure actually in the position of the monsoon fronts, the Chama fronts. Okay, so even though the large area experience cooling is unfavorable to convections. So you should see less convections. But in localized area here, the Chama front area, you do see enhancement of the convection. So this is the precipitation change. Okay, the brown color indicates the reduction in precipitation, and the blue is increase. So you see, most of the area has a reduced precipitation. However, in this area, in the position of the Chama front, the main front, you see a slight increase in precipitation. And that is through the change of the wind field and circulations. We call it dynamic feedbacks. Another evidence of this is dynamic induced is that this is a vertical profile of temperature and vertical winds. The vertical axis is the height, and the horizontal axis is the latitude. And the color means the change in temperature. You see, most of the troposphere are cooling, experience cooling, the blue color. So cooling means the air should be more stable. However, you see enhanced vertical motion updraft here at this location. That is through dynamics, it's not thermodynamics. Another thing I want to mention is this area here. This area, because of the enhancement of the Pacific high, so enhanced easterly here, and that easterly encountered the original westerly, so it kind of weakened this westerly. And what is this originally? We go back. What is this strong wind system? That is the summer monsoon, bringing the moist air from the Indian Ocean to East Asia. And this summer monsoon is being weakened because of this dynamic figure. Okay, now I move to this second example. I'll shift to the winter time. And in the northwestern Pacific Ocean, wintertime, there's a special phenomena called cloud streaks. Okay, from this figure, you can see parallel line-shaped clouds. And those clouds are formed because the cold continental dry air moves to the ocean. Initially, you don't see cloud because it's very dry, but gradually acquires water vapor and heat from the ocean surface. And after some distance from the land, you see the development of the clouds. And because the air moves very fast, so the cloud tend to be parallel line shaped. And notice that this area also is downstream of the major emissions. So of course, the emission on the land certainly get into these line clouds, the cloud streams. So we're interested in how those clouds being affected. And this is use a regional model simulation. This is a satellite picture. We choose this area with focused experiments. Okay, and this is the same model domain here. And try to skip the details. The main thing is that we did several sensitivity on the aerosol over this region. And the control run is the yellow line here. It's representing the clean continental background. And we increase the concentration by 10 and 100 times, or decrease by 10 and 100 times. So covering the pristine marine conditions or covering the very polluted conditions. So in the following, the symbols here, N100 means 100 times the control run. N10 means 10 times control run, etc. On the left, this is the satellite picture of the zoom out section of the cloud streets. And this is our simulated cloud area. You can see the dimension of the clouds are very similar. So in general, we did a good job in simulating those clouds. And this is the vertical profile of the microphysical property in the cloud. The vertical axis is the height in pressure coordinate. And the horizontal axis here is the cloud number concentration. So you can see this is the cloudy area. About 970 millibar to about 820 millibar. This is the cloud depth. And you can see clearly more aerosols cause more cloud drops. And that will cause the cloud drop to reduce their sizes and reduce the collision probability and reduce the formation of raindrops. Or in here, because the rain is very weak, we usually call it drizzle. Okay. So from the right panel here, it's indeed in the cloud water is higher for more polluted conditions. And very low in the pristine conditions. That is because in the pristine conditions, the drizzle is very easily developed. But with the additional aerosols, the drizzle is suppressed. And that has many important consequences I will discuss later. And these are the cloud albedo changes. The vertical axis is the latitude, and the horizontal axis is time. So it's an evolution of the cloud system, average longitudinal. Okay, and these are the clean case and this is polluted case. You can see very distinct difference between the albedos of different aerosol concentration. For example, in the polluted condition, the highest albedo can reach 0.8. But in the clean conditions, the same location, the albedo is only about 0.3, 0.4. That's a huge difference. And that certainly affects the radiation budget in this area. And this is the average, domain average. You can see also a huge difference between clean and polluted conditions. So short summary is aerosol enhanced albedo and therefore can cool the surface. Another effect is from the drizzle. I mentioned that aerosol can suppress the drizzle productions. And drizzle, when you fall below cloud, it will evaporate. That will cool the surface. So if you suppress drizzle, there's no drizzle cooling here. So you see below cloud, the temperature is higher. The evaporation rate is lower for polluted conditions. So the temperature is higher on the surface. And the situation is different in the cloud, okay, because of the removal of water vapor. I will only get into details. But in any case, from the clean case to the polluted case, you'll see a change in the vertical profile temperature that changes the stability of the boundary layer. So we actually make the boundary layer unstable because the lower level is warmer, upper level is cooler. So the boundary layer becomes more unstable with the input of aerosols. And the water vapor, we use the equivalent potential temperature. That's only difference is mainly from the water vapor. So indication of the water vapor change. So in cloud, the total water vapor decrease because of drizzle, okay, in the clean case. And drizzle also provide water vapor below cloud. Okay. So the main message is that drizzle effects, drizzle suppression by aerosol will change the dynamics in the boundary layer and change the wind field. So here indeed we see that this is the vertical wind probabilities. Okay, this is the wind speed, here is 0, and these are downdraft, these are updraft, and this is the height. Okay, so you see the clean case, the probability distribution is like this, and with the average aerosol condition is similar, but you see broader up and down objects in the near the cloud level there. So there's an indication of change in the turbulence. And this is a horizontal wind speed. Okay, I marked it 8 meters per second with the red line here. Okay, so this is a clean case. And in the polluted, more polluted case, you see the wind become weaker. Okay, become weaker. And that has this is the difference. You see, increased positive winds, the wind speed shift to lower conditions. Okay. And the change in wind speed certainly influenced the evaporation of the ocean. So that influenced the airship exchange in this area. And that combined with the radiation effect, it certainly can affect the regional climate here. But I won't get into the further details. Okay, now I'll come to the second part of my talk, the effect of aerosol on weather and precipitation in the shorter time scale. I'll give you one example in the winter convection and one for the summer convections. This same similar diagram in the cloud street condition in the winter. Okay. This cloud, as I mentioned, gradually developed in the dry air from continents. So the clouds actually quite shallow. Usually we don't expect a lot of precipitation produced from those clouds, mostly drizzle. Okay. However, you see in this news, can we take this out? In this news, it reported a huge snowstorm in Hokuriku region in Japan. Here, you can see it's directly downstream of the cloud streets. When the cloud street area encounter the topography, with the orography effect, it produces huge snowfall. Okay. In Taiwan, here, you can see it's also downstream of the cloud street development. In the northern Taiwan, we do have a lot of cloud influenced by the topography. And actually, we also have very strong precipitation associated with this kind of boundary system. So this seemingly effective clouds can actually produce a lot of precipitation. And how much we can look at the next diagram. Usually in the winter, we don't expect too much convection. So if there are precipitation, there are usually stratiform cloud with slow drizzles. However, if you look at the December records, this is the December record in Taiwan, the climate average. We do see some enhanced rain due to the topography influence with the, again, downstream of the northeasterly flow. Okay, and the peak is around 400 millimeters. That's actually quite a lot in 1 month. Okay, and in year 2020, 1 month, you see over 1,000 meters of rain. That's a huge amount. And why? Okay. Of course, firstly, this is associated with this winter monsoon, shallow clouds, but enhanced topography effects. What happened in year 2020? This is a record high. Why? And I checked record. In year 2020, there's a La Nina occurred in this region. So it may be associated with La Nina. But the La Nina in 2020 is not particularly strong. It happened in the past many times with similar strengths. So there must be something else happening in 2020. So what is it? I think now everybody blame everything to COVID-19. Okay. And I think actually it might be the case for year 2020. Why? Okay. If you look at this scattered cloud, the vertical axis is the monthly precipitation, and the horizontal axis is monthly mean PM2.5. Although it's quite scattered, but you still see a trend. Okay, stronger precipitation associated with lower PM2.5, but it can be the other way. Okay, what is the cause? What's the effect? We don't know, but they might be positively related. So more rain can wash out aerosols to produce lower PM2.5. But the other way around, lower aerosol actually can produce higher precipitation. Okay, so we did a simulation of pick a case in the November 23rd. So we simulate this small area of clouds here. And the top panels are observations from Central Weather Bureau and the composite from the National Center for Disaster Reduction. Okay, you see two areas of strong precipitation with steady precipitation exceeding about 130 millimeters here and here. Okay, and the three panels below are simulated precipitation. In the beginning, the Central Weather Bureau asked me to simulate, and with typical model setup, we cannot produce very strong precipitation. Usually it's like this, or at best it's like this. The peak precipitation only is 30 millimeters. But we did some experiment on the aerosols. We reduced to the very clean case. You see, the precipitation is quite near what's observed. So I think there's a possibility that COVID caused the reduction in emission in East Asia. and make the air cleaner, but the cloud precipitate more efficiently. Okay. But that's just a hypothesis. We haven't get a direct proof yet. So a short summary of the aerosol effect on the precipitation. Our results actually generally agree with the finding observations. This is a analysis by Tao et al. They show that in the global warm clouds, the different color, the gray shades indicate the stability of air and the cleanness. So darker color means, let me see, the top two are more clean or stable, and the bottom unstable or dirty. Okay, and the message is that when the air gets dirtier, you get less rain, even if the liquid water content in the cloud is the same. These four columns have the same liquid water content in the cloud, same water amount, but the precipitation is different. Okay, and the bottom diagram shows that the probability of precipitation actually decrease with increasing aerosol. Okay. The example I show is in the winter. Now, how about deeper clouds occurred in the summer, which may have what we call the cold rain process. That is the microphysical process involve ice particles because the cloud is high enough, and the upper level temperature may be quite low. Before I get into details, I show you this summary of aerosol effect from different cases. Okay, and please ignore the axis here. You only have to know that above this diagonal line, the precipitation decrease with increasing aerosol. Okay, P means precipitation, M means aerosol concentration. Okay, so for this cloud systems, aerosol decrease precipitation. However, we do see a lot of cases here that increasing aerosol produce more precipitation. And if you look at it more carefully, those are mostly convective clouds, deeper clouds. So we suspect that these deeper clouds respond differently than the shallow clouds, than the warm clouds. One of the possibility or the hypothesis is this. They call it the aerosol convection invigoration effect. Let me explain it briefly. Okay, this is a clean cloud. So the cloud develops precipitation quite efficiently. So not until the cloud is too high, the precipitation already formed and remove the water. Okay, so the cloud dissipates quickly. Now with the input aerosols, the aerosols suppress the formation of rain, suppress the rain formation. So most of the liquid cannot fall out of cloud. They keep it in the cloud and being lifted above the 0 degrees sea level. Then those extra water may freeze at the upper level to release latent heat. And that extra latent heat will help the convection, so make the convection stronger. So even if the initial precipitation is suppressed, but later on, because of development of the convection and the ice particles, that you might have more precipitation form. So is that case in Taiwan? I simulated a lot of summer convective storms in northern Taiwan. And this is a 10 case studies. And I do the sensitivity test with clean aerosol, average aerosol, and polluted aerosol. Okay. So on the left, you see that this is the average rainfall. It's not spread, but the mean is similar. So our study shows the aerosol doesn't affect the total precipitation, overall precipitation. However, if you look at the specific locations at the peak accumulation, the largest accumulation, it increases. And the hourly intensity also increases. And that agrees with the convective invigoration effects. So it that in our area, I think the aerosol does affect the cold rain processes and cause the rain to be more concentrated. These are another example. I just show you the simple diagram of the evolution of precipitation with time. Okay, this is a case in the Central United States. Okay, this is a precipitation evolution with time. In the observation, you show initially a very small peak, then a big peak here. Okay, now with the clean case model, the blue line here, you see initially the precipitation peak is taller, but later it's weaker. But if I switch to a more polluted condition, the initial precipitation reduced, but the second peak increased, more like the observation. Okay, and we see a lot of cases like this. For example, this is the case in Taiwan. You also see the polluted case, the record here, initial peak reduced, but the later peak enhanced, compared with the clean case. Okay, and the green case is another option from the model. Many people use that, but those models usually cannot produce the weaker first peak and the stronger second peak. So with this example, I show you that the summer convection may behave differently in response to aerosol. And also the aerosol change the timing and the intensity and the locations. But these are mostly a single cloud system. A lot of people argue that, well, if the cloud doesn't rain here, it might rain downstream. It compensates. So the overall, over a larger region, can you still see the aerosol effects? Okay, and the last example here, I'll show you condition occurred in southern China. In southern China, they observed a decrease in precipitation from the 80s to this decade. Okay, significant decrease. And what happened here? There might be some climate-related issues, but how about aerosol? Because from the 80s to the year 2000, the aerosol concentration in China increased quite a lot, especially in southern China. So you see the recent decades, year 2000 to 2011 is in red, and the 1980s is in blue. And this is the intensity distribution, probability of intensity. Over here is higher, stronger precipitation, here is weaker precipitation. And the weaker precipitation probability becomes higher with pollution and becomes lower with aerosol. So which means aerosols will increase light rain but decrease strong rain in the whole southern China. And we used the also numerical model to simulate the effect. And we found that this is the rain intensity distribution, and similarly the blue curve is cleaner case, okay, and red is the dirtier case. And we see the whole spectrum shifted with the aerosols. And the final conclusion is here. The polluted case produced less precipitation compared with clean. And that occurred both in year 2010 and the 2000, okay. So the result shows the effect, but what is the mechanisms? And within the mechanisms like this, it's also an indirect effect. In the whole southern China region, the clean case you have less because of the more effective precipitation, then the cloud dissipates faster, and then the cloud doesn't reflect sunlight. But with more aerosols, the cloud itself reflects more sunlight, and also the cloud dissipates less. So you have more cloud cover, and that will reduce the surface radiation, cause the cooling of the surface temperature. And that cooling stabilizes the atmosphere. So let's make the convection weaker for the whole area. So in summary, we show that the anthropogenic aerosols have a significant effect on the global radiation, and that has an effect on the cloud system, and that effect can produce feedback, dynamic feedback, because it influences the surface temperature, then influence the wind pattern and circulation patterns, and it has some certain consequences of air-sea interaction because of the dynamic feedbacks. For the convective clouds, we see that also affects the heavy rain. Okay, in terms of the intensity, okay, the stronger rain gets stronger, weaker rain gets weaker, and also the timing. The stronger rain may produce later. Okay. And the wide scale effect of the indirect effect may cause the cooling of the surface, stabilize the atmosphere, which results in the whole area to be less convective. So the whole area is a less precipitation. Okay, that's all my talk. Thank you.
Thank you very much for the very nice talk. I think this is a very nice summary of the complex and inhomogeneous effects of aerosol on clouds and precipitation. So now we have about 10 minutes for discussion and any question from the in-person attendees from the conference room? So please.
Professor, thank you for your wonderful presentation. And in your slide, one of your slides shows an aerosol effect on summer external convection rainfall.
The online audience might not hear you, so please come forward.
Okay. The presentation, in particular heavy precipitation, can remove the aerosol in the atmosphere through the wet deposition. So how do you avoid the impact of the wet deposition in this case?
All these cases aerosol are coupled. So we do have the scavenging effects. Okay, but for these cases, the duration of the cloud is short, so there's only influence one life cycle. But if you talk about the long-lived clouds, like the last case, the regional cloud, the mesoscale convective system, then that will feedback to the clouds. Yes. So there's one hypothesis that if the aerosol concentration is reach a certain threshold, then the whole precipitation stops. Yeah. Then there'll be no wet removal. So the aerosol keep in the air, and that will shift the climate to another mode. It doesn't come back anymore. Okay, that's a very interesting, we call it biostability hypothesis. The climate will stay in the polluted mode or the clean mode. If you want to stay in the clean mode, the aerosol must reduce below a threshold.
Okay, thank you.
Okay, thank you. Any question from the in-person attendees or from the online attendees? Any questions? No? I have a question in chat. Okay, can you lead or?
Yes, I can read. Yeah.
Okay, could you please explain more about why heavy rain decreased due to the increase in aerosol?
Okay, I think you're talking about the last example. The last example is through the indirect effect on radiations. So the aerosol increased the cloud reflectance. And so the less sunlight reach the surface, so the surface become cooler. And that will reduce the instability. That make the boundary air more stable. More stable air means less convection. So that causes less precipitation. Hope I answered your question.
Is that okay for you? So any question from the room or from online, or perhaps you can use chat to ask questions. Any question from the in-person attendees? I'm afraid I can't see the room, but any questions? Okay, from online, Professor Takemura, please.
Yes, thank you for your very interesting presentation. So I have a technical question actually. So the you show the result of the sensitivity experiment of the on the heavy rain, Aerosol effect on heavy rain. So could you explain in more detail model setting, especially for the horizontal resolution, and how to express the aerosol cloud interactions?
Okay. The model resolution is about 1 kilometer horizontal. In the vertical, we use, I forgot, because different cases, I use different vertical layers, but it is between 40 and 50 layers. And the model is the Wolf model, the weather research and forecasting model, that is community model. However, the cloud microphysics is modified with our own, the NTU option. Now it is an official option of the Wolf, the option 56. And that microphysical parameterization has very complete interaction with aerosols. So we do simulate the activation of aerosol into clouds. And also the aerosol contained in the particle that can recycle back to the atmosphere. So we will consider the full cycle.
Okay, thank you very much.
Thank you.
Okay, any questions from the room or from online?
Sorry, I actually missed your talk in between, but I just think about one thing, because you talk about hygroscopicity and also application to the model. So it reminds me one thing about the virus. So I just kind of try to understand where, because that is also one of my research topic. Well, the bioaerosol from all spec, like marine aerosols also, one of it should be bioaerosol. Will that change the RAM pattern, or how do you take care of the activity like hygroscopicity, or for those kind of bioaerosols?
Okay, thank you. The question is about the effect of bioaerosols, like pollens and the phytoplanktons and so on. We did have some simulation on the effect of the bioaerosols. The main effect is the ice nuclei. Okay, they can help the production of ice in the cloud in very quite warm temperature. Okay, normally in the normal atmosphere, the cloud water doesn't freeze in the sub-zero temperatures, unless the temperature is lower than about 35, 40, minus 35 or minus 40. So we call it super cool water. And for those cloud water to freeze, you need to have ice nuclei. And the bioaerosol is one of the effective ice nuclei. Actually, the most effective natural ice nuclei is bacteria. Okay. And for pollen and the phytoplankton, they are less effective, but they can be quite abundant in the land areas. So our simulation do show that it can affect individual clouds very efficiently. They enhance the precipitation formation efficiency. However, we did simulate the effect of ocean phytoplankton effect on typhoon, on hurricane formation. And initially they have some effect, but eventually the effect is dissipated because if you keep the water in the cloud, eventually they will fall in the typhoon system. So typhoon is a thermodynamic control system. Okay, so it depends on the cloud systems.
Okay.
Sorry, I probably forgot to introduce myself. My name is Kachi, so I'm from Metropolitan University also. So because you say bacteria is probably the most like hygroscopic or to be active as a CCN. Well, they alive or dead inactive make difference for acting as a CCNC dead.
There are some effects. I'm not sure about the details, but you know, in cloud city, some people use dead bacteria. Okay. I think from what I read, is dead bacteria still are effective because the effect is from the protein, functioning protein. It's not from the whole bacteria. So if it's dead, the functioning protein is still there. So even it's dead, it's effective. If you go to the snowfield in US or Europe, some of the snowfields will use the bacteria to produce artificial snowfall on the snowfield. They use bacteria, actually, but dead ones.
Okay. It's almost time, and so I would like to close the discussion. Let's thank again Professor Chen for a very nice talk.
Thank you.
And let's move on to the next talk.